Yes, welcome to continuation on spring constant, that is Oak's law. Yes, now we may proceed. Uh, we're having these parts, but before we move to exactly the spring constants, therefore we can give out some examples. And I'll give out an example that goes like the figure below. Yes, that is now the diagram. We are told that the first spring, when it is on its own, uh, it can be of a total length of 5 centimeters. And when it is having a certain mass of 80 grams, then the total length will be 80 centimeters, 10 centimeters. And when a stone is hanged, it is going to have 8 centimeters. Therefore, we are entitled to do our own calculations and work out what will be the mass of the stone. Therefore, we can do the solution here. We all know that spring constant is given by force over extension. Therefore, let's use the hot spring when it is having no mass and when it is having a mass. Therefore, we'll say that our extension here will be uh, 10 centimeters minus 5 centimeters, and this one we arrive at 5 centimeters. And this one is equivalent to 0.05 centimeters. Uh, the mass that is being hung here, mass is the same as 80 grams. We want to convert this mass into weight, where we'll say force is given by mass times gravity. This one will be 80 divided by 1000 times 10 newtons per kg. And this one will lead us to allow me to compute. Divided by 1000 times 10. This is 0.8 newtons. Therefore, because we're talking of the same spring, then now we can say that the spring constant is equals to 0.8 newtons divided by an extension of 0.05 meters. So this one is supposed to be in meters. And this one will hand us to 16 Newton per meter, like that. Then now, for the second case, once you arrive here, since the spring is the same spring, which is holding the stone, we'll say that since now we have K as 16 Newton per meter, now let's look at extension. In this second case will be 8 centimeters minus 5 centimeters, which will be 3 centimeters. And in this case, the 3 centimeters will be the same as 0.03 meters. Therefore, from K is equals to force over extension, then our 16 will be the same as the unknown force over an extension of 0.03. Therefore, our force will be the same as 16 times 0.03, and this is 0.48 newtons. Now for this, we'll ask ourselves, if force is given by mg, what about mass will be given by F over g? Therefore, this will be 0.48 divided by 10 newtons per kg. This is 0.048 kilograms. And this is equivalent to 48 grams. So this is the weight, the mass of the stone. We can now declare and move on to combined spring constant. And we'll start with series connection. Then, as usual, I usually say consider two identical springs that are connected in this manner. This is S1 and this is S2. But S1, S2, these are springs, they are identical. Therefore, we need now to move on to derive on the way to work out on the spring constants. When it is like this, uh, the moment you're having these springs in this manner, each spring will extend independently. Therefore, you can say this one extends by E1 and this one extends by another E1, which is independent. Therefore, we'll say that E total extension for the system will be E1 plus E1. This is same as 2E1. But remember the formula of calculating the spring constant, F K, sorry, is given by force over extension. Now here we need, this one you can say ET over ET. This is for one spring, for a spring, you can say E1 there. Therefore, now if you want to get what we call the combined spring constant, it will be the acting force of E total. Therefore, our combined spring constant will be the same as F E total ndio hii iko hapa, which is 2E1. Therefore, we'll say that but F over E1 is same as K. And the K is the spring constant for one spring. Spring constant for one spring. Therefore, if you look at these parts, is still this one. Therefore, if we substitute this F over E1 with K, we'll say that our combined spring constant is same as K over 2. In short, combined spring constant in series is the same as the spring constant of one spring divided by the number of springs, where n is number of springs. And that is the conclusion. Now we may proceed to the second one when we are having in parallel connection. So now we can say now in parallel connection. Consider when you're having two springs, like that. Uh, these two springs here are sharing this force, meaning that if one spring could be extending by E, then the total extension for the system will be the same as a half of the extension for one spring. Therefore, we can say that before we move on, we can say that E total for this one is given as a half E1. Let's get to the whole formula that K is given by force over E1. But now here we are talking of E total is same as a half E1, meaning that these two springs have shared the extension that could be for one spring. That's why we say in parallel connection, we expect that they offer some strong resistance to the force applied or the weight that they will be subjected to. Therefore, now we go to combined spring constants will be the same as force over Et. Remember these are two where we'll say that Kc, which is combined, will be force over half E1. If we proceed, we'll say that Kc is the same as 2F over E1. But if you remember that we are having this equation here, where it is representing K, will finally land at Kc is the same as 2K. This part, it is the one that is here. So we substitute with K. When we are using two springs, then we'll find that in parallel connection, the spring constant, the combined spring constant is the same as twice the spring constant of one spring. Therefore, in conclusion, we can say that Kc in parallel is the same as Nk. That is what we can conclude. We may proceed now to have some examples. Allow me get a question on the scene. where you are told this is example 2. 2 very light identical springs P and Q are arranged as shown. A weight of 4.8 newtons is supported by each arrangement. Given that the spring constant for each spring is 10 newtons per centimeter, then you have to determine the extensions for each arrangement. The first arrangement is like this. And that is 4.8 in newtons. Then now you are supposed to get the total extension. Determine the extension for each arrangement, meaning that we are looking at the effective extension. Therefore, we know that spring constant is 10 newton per centimeter. And this is equivalent to, we said we divide by 0.01 or we multiply by 100. This is equivalent to 1000 newton per meter. Therefore, we know that for this case, we shall have combined spring constant, which will be K divided by N. So this is 1000 divided by 2. Therefore, the effective spring constant here will be 500 newton per meter. From that, now we say that combined spring constant will be given by the force over ET, and we are having 500 newtons per meter is equivalent to 4.8 divided by E total. Therefore, ET will be the same as 4.8 divided by 500. Therefore, 4.8 divided by 500. 4.8 divided by 500. This is equivalent to 9.6 times 10 raised to -3 meters, which is equivalent to 0.096. Sorry. 0.0096 meters. This one is equivalent to 0.96 centimeters. Our second arrangement is when they are in parallel connection. Therefore, in this case, uh, our combined spring constant will be the same as n, the spring constant of one spring. Therefore, Kc here will be uh, 1000, that is 2 times 1000, and this is 2000 Newton per meter. Therefore, Kc is same as force over E total. And this one will say it is 2000 is equals to force of 4.8 divided by 2, divided by E total. Uh, E total will be the same as 4.8 divided by 2000. And this one will come down to 2.4 times 10 raised to negative 3 meters. And this is equivalent to 0. This is equivalent to 0.0024 meters, which is 2.4 centimeters. This one may bring a lot of worry, is as how have we got to have it worked in this manner? But trust me that there are so many ways of working out and arriving at the answer. So we can have other alternatives. I go slowly with these alternatives. Uh, Therefore, I'll proceed. Option 2. Spring constant for one spring, we have said that it is 1000 Newton per meter. Then we say picking an individual spring. Then K will be given by force over extension. Ile tulisema he1. Therefore, 1000 will be the same as a force of 4.8 divided by E1. Then E1 becomes 4.8 divided by 1000. There is 0.0048 meters, which is equivalent to 0.48 centimeters. Okay. But now we say that E total will be E1 plus E1, which is 2E1. Therefore, EP will be 2 times 0.48. This one will arrive at 0.96 centimeters. For case 2, uh, just need to say that the effective uh, E total for this one will be the same as E total for this one will be the same as E half E1. Therefore, from K is equals to 1000 Newton per meter, and our force is 4.8, then our E1 will be what? Therefore, our E1 will be force over K, which is 4.8, divided by K, which is 1000. And this is 0.0048 meters, which is equivalent to 0.48 centimeters. Therefore, E total, which was the same as half E1, now we'll say that half of E1, then we'll arrive at 0.24 centimeters. There is no difference. When it is like this. This was supposed to be uh, 0.24 centimeters. And if you link it directly, then it is gotten here. Then now without stress, that is the way to do that part when it comes to the combined spring constant. Let's check if you're having another question. We'll still touch on things to do with the graphical analysis, but that one will be done later. Having nothing else on that, I can just give out a further example. So we can give out example 3. We thought that for the system below, is of identical springs. Given that the system produces an extension of 20 centimeters, determine the spring constant for each. Then here is the diagram. These are two springs. We are having a rod here. This one is of 20 newtons. Then we have a third spring, and it is anchored on 20 newtons. Then now, from this one, you're supposed to get the spring constant for each, since they are identical. In this case, these two are in parallel, but in series with this one. You should also need to understand that this rod is having a weight of 20 newtons, and we still have another hanged weight here of 20 newtons. Therefore, what does this one tell us? For the parallel, the acting F will be the same as 20 newtons plus 20 newtons. It will be 40 newtons. This and this. For the single spring, F will be the same as only 20 newtons. Then we say we're having this one, we let it produce an extension of E1, and this one here to produce an extension of E2. Therefore, we'll say that this one will be having a combined spring constant, so that it produces E1. So for the upper part, we'll say that for parallel, we'll say that combined spring constant will be given by force over E1. Therefore, in this case, our force here, okay, you can call this one equation 1. We want to make E1 the subject formula, therefore E1 I think it will be okay. Our Kc here will be 2K. So I think now I can make a second equation. which will be 2K is now the same as F over E1. Since we are talking of the effective extension for the parallel connection, which is E1, this becomes equation 2. E1 becoming the subject formula, it will be F out of 2K. Can say equation 3. Then for the single spin, then K will be the same as force over E2. Making E2 the subject formula, it will be F over K. You can call this one equation 4. Summing up, summing equation 3 and 4, E1 plus E2 will be the same as 20 centimeters, which is equivalent to 0.2 meters. That is effective extension for the system. Then now we can proceed. And in this case, we'll say that F over 2K plus F over K is equals to 0.2. But now, the F for this, we said it will be 40. It will be 40. Therefore, it is now 40 out of 2K plus 20 over K is equals to 0.2. If, let me shorten this so that I use the same space. We're saying that this is 40 out of 2K plus 20 out of K is equals to 0.2. This means that 20 out of K plus 20 out of K, we have divided because we are having 2 here, is equals to 0.2. Multiplying through by K, it will be 20 plus 20 is equals to 0.2K. This is 0.2K, which is equals to 40. Therefore, our K will be 40 divided by 0.2, and we arrive at 200 newtons per meter. That is the way for that working. It is simple. We may also have several others which are not that much complicated. For example, should we call this one our example 4? We thought that a mass of 100 grams is suspended from a lower end of a spring if the spring extends by 100 mm. and the elastic limit of the spring is not exceeded. What is a spring constant? So now we are being offered a solution for this one. So we are applying the Hooke's law from F is directly proportional to E. Therefore, we want to look at the spring constant. So in this case, let me do it aside here so that we may move with the same language. What is the spring constant? So we know that mass is 100 grams. Our force will be mg, which is 100 divided by 1000 times 10. This is leaving us at 1 Newton per, 1 Newton. Like that. Our extension is 100 millimeters. This one in SI unit is equivalent to 100 divided by 1000. So that you get 0.1 meter. Therefore, for us to get the spring constant, K will be given by force over extension. And this one is from 1 Newton divided by 0.1. And this is 10 Newton per meter. Like that. We still have another question. We may call it example 5 for this case. A metal cube suspended freely from the end of a spring causes it to stretch by 5 centimeters. That is when we are having a metal cube. Then you are told a 500-gram mass suspended from the same spring stretches it by 2. I think we are supposed to talk of 2 centimeters. If the elastic limit is not exceeded, find the weight of the metal cube. The first thing, when you're having a question like this, is like you're comparing two weights. Then you need to say that, let's pick when we are having the known mass and the extension. Taking mass as 500 grams, then our weight or force will be 500 divided by 1000 times 10. And this one will lead us to this one is going to lead us to 0.5. Sorry, 5 newtons. Like that. Therefore, our extension here is the same as 2 centimeters. This one in SI unit is 0.02 meters. Therefore, our spring constant for the spring will be given by force over extension, which will be 5 newtons divided by 0.02. And this one will lead us to 500 divided by 2, which is 250 newtons per meter. But now in this case, now we are having the cube. When we are having the cube, we are having extension of 5 centimeters, and this is equivalent to 0.05 meters. Uh, the K which you have gotten there will be 250 Newton per meter. Then now we're supposed to ask ourselves, what about F? Therefore, our F will be the same as KE, which is 250 times 0.05. 250 times 0.05. And this is giving me 12.5 newtons. If we proceed from F is equals to mg, then our 12.5 will be the same as the unknown mass times 10. Therefore, our m will be 12.5 divided by 10. And this one we arrive at 1.25 kg. Remember, the question is asking us, okay, we are supposed to arrive at this point. So this one, we can cancel it out. But it will be of importance in case you are asked about the mass. So when you're having a 1.5 kg mass, this will be from mg. So that we arrive at 50 newtons like that. Then spring constant, we still have it here. Then from the working and the calculations, we'll arrive at 0.06 meters. And at this junction, we may close. We may close so that we may prepare for the tomorrow's parts. Tomorrow I'll probably may not promise that it is tomorrow, but the next lesson we are likely to look at things to do with the working in a ticker timer. Don't forget to subscribe. You can always reach me through this number. This is KH1 Online School. Share widely with friends.